Hello everyone. Welcome to LatentQuant. This channel is about the systems beneath finance, not trading strategies or predictions. I'll sometimes simplify things to focus on intuition. And if you can catch a mistake or a missing nuance, feel free to point it out in the comments. Alright, let's get started. Okay, so let's start by answering a basic question. Why queues matter? When people think about trading systems, they usually think about math, models, or signals. But in practice, most trading systems spend far more time moving data between components. As you can see in this short animation, there are different components like market, where the data comes in, and there is strategy component, where the data from the market component comes and it's processed further to generate the signals, and then it's passed on for the execution. So each handoff between these stages adds latency and jitter, and those handoffs are mostly implemented with queues. That's why queue design ends up mattering far more than people expect. Okay, now that we know why queues matter, let's start discussing about SPSC. SPSC stands for Single Producer, Single Consumer Queue. It means exactly one thread processes the data and exactly one thread consumes it. No fan in, no fan out, just a direct handoff between those two threads. Most SPSC queues are implemented as ring buffers, a fixed size array where producer advances a tail index and consumer advances a head index. Conceptually simple, and that's the simplicity. Okay, now that we know why queues matter and what is SPSC, let's talk about the underlying implementation of SPSC, and it's done by ring buffers. So ring buffers are basically a circular data structure, but physically they are just linear arrays in memory. The buffer itself is contiguous, which means predictable memory access and good cache behavior. So as you can see on this short animation at the right, so we have logical implementation of ring buffer, where basically the producers adds on the data and it's mapped directly to the physical memory. And it's basically a circular, so we use a modulo operator to go back on a circular loop. From the CPU's perspective, this still looks like sequential access to memory, which modern hardware handles very efficiently. So why do people go out of their way to design systems around SPSC queues, and why is it so appealing? The short answer is that SPSC queues align extremely well with both hardware and system architecture. First of all, ownership is static. The producer owns the tail index and the consumer owns the head index. There is no competition over who gets to update what. The queue can make progress using simple loads and stores. Secondly, the underlying data structure is fixed size ring buffer, as we discussed already, which is physical contiguous in memory. That gives you good cache locality and predictable memory access pattern, which modern CPUs handle very efficiently. The key point is that SPSC queues are appealing not because they are clever, but because they remove unnecessary sources of unpredictability from the system. Okay, so let's discuss about the use cases of SPSC. Trading systems naturally form single producer, single consumer relationships. A network thread hands packets to a parser. A strategy thread hands order to an execution engine. A strategy thread hands events to a logging or whatever post trade analytics. In each case, there is a clear owner on each side of the handoff. SPSC queues fits this structure perfectly and provide predictable latency. Okay, now we have talked about all the pros of SPSC. Let's talk about some cons. It's very tempting to think that because there is only one producer and one consumer, an SPSC queue is automatically thread safe. That assumption is wrong. It's because of CPUs and compilers reordering. Compilers and CPUs are allowed to reorder operations, and writes made by one core are not guaranteed to be visible immediately to other. Without explicit synchronization, there are no guarantee of ordering and visibility. SPSC removes contention, but it does not remove the memory model. Let's discuss about the CPU reordering. As you can see on the right side, we have a core where we have two variables, data and ready, where basically we are trying to write the data and signal that it's ready for consumption. But due to the optimization done by CPU and compilers, the ready can be updated first and then the data is written on later on. So in that case, the consumer can still see the stale data. Alright, now that we have got a fair idea of what SPSC is and why it matters, in the next video, we'll make this concrete. We'll write an SPSC queue that looks completely reasonable, clean logic, no obvious bugs, and we'll watch it fall in subtle ways. Then we'll fix it step by step, firstly by using mutexes to establish correctness and then using automix to recover performance. Thanks for watching. If this kind of system level thinking is useful to you, stick around and share and subscribe. See you in next video.